So far, we have talked about AVL, deletions, insertions, and deletions, and characterize them. Okay. But we still have not proved whether all this effort is required, is really required. Will work only if we can prove that the height of the AVL tree is log n, where n is the number of nodes. So that's what we're going to try and prove now. So this should be proved for a tree with minimum number of nodes. Okay. So let's start with this. I have a tree with one node. Then this is AVL, yes. Okay. Now I have a tree with two nodes. This is AVL, balance factor is -1 here, 0 here. Now, what I can do is I can create a new tree by making these two trees which we saw subtrees. Let me call this N0, tree of height 0, tree of height 1, and this is tree of height 2. Notice that we just took the tree of height 0, put it here, tree of height 1, put it here. Similarly, I can do a tree of height 3 by taking, this is one AVL tree. I'm just constructing from one side. You can construct from both sides. I mean, you can have the mirror image without any problem. Now, this one has balance 0, plus 1, plus 1, plus 1, 0, minus 1. Okay. This is again a tree with minimum number of nodes. Let me call it N3. Let's now again, what did we do? We took this tree and this tree and made a new tree. This tree goes over here, and this tree goes over here. So it's interesting that we can generate a new AVL tree from previous new AVL tree of height h plus 1 from previous trees of height h and h minus 1. Okay. So in general, we can write that if I have an AVL tree of height h, then it consists of nodes in height minimum tree. One subtree is height h minus 1, another subtree is height h minus 2. Okay, and we add an extra node. So let's count this. This is 1. So if you start with N0, N1, N2, N3, N4, you see that N0 is 1, this is 2, this is 3, N2, sorry, N0, N1, sorry, N2 is 4, and we have in 2 is 4, and this becomes 7, and this becomes 12. I hope it rings a bell for you. So when we start out, for example, we have, let's look at, it has a close relationship to the Fibonacci sequence of numbers. And so the Fibonacci sequence of numbers, we have 1, 1, 2, let me call this F0, F1, F2, F3, F4, and so on. So when I look at N0, it has one node, and therefore this is equal to F2 minus 1, number of nodes. And if you look at N1, equal to 2, which is F3 minus 1. Similarly, N2 is, one moment, N0 is 1, so N2 minus 1, N1 is 4 minus 1, 3, and N0 is F1, F2, sorry, yeah, F2 minus 1, yeah, N2 is F4 minus 1, and so on. So in general, we can write number of nodes in a AVL tree of height edges f h plus 2 minus 1 for h greater than or equal to 0. From Fibonacci theory, fh can be approximated by what is called the golden ratio to the power of h divided by root 5. P is equal to 1 plus root 5 divided by 2. So I have now nh can therefore be approximated by p to the power h plus 2 divided by root 5 minus 1. Now nh equals okay, plus 1 equals p h plus 2 divided by root 5, or we have root 5 into nh plus 1 equals phi h plus 2 by root 5, or we have h plus 2 equals log of phi to the base p of root 5 of nh plus 1 minus 2. Oh, sorry, here, or h is equal to log to the base p of root 5 of nh plus 1 minus 2. Now phi is approximately 1.44. Therefore, the AVL tree is of height log. Okay, so this way. Okay, and of course, it doesn't matter anyways, it's only a constant that changes. So this completes the proof for the height of the AVL tree being of height